As you might know, the electrical energy in my garage is created by solar energy, which on the other hand is getting stored in a big and heavy lead-acid battery. Only problem is that the original capacity of this battery decreased noticeably over time. That is why I've been searching for more modern alternatives to this energy storage problem. And what I found was the Tesla Powerwall, which is basically a container filled up with batteries, an inverter to supply mains voltage, and a cooling system. But honestly speaking, I don't need the inverter, nor a capacity of 13.5 kWh, and I especially do not want to pay $7,600 for it. So in this video, I will be showing you how I created my more or less crude but still functional DIY Powerwall. Let's get started. This video is sponsored by JLC PCB, whose offices were visited by more than 100 customers in the past year. And you can meet them as well at the Maker Faire in Rome this year, where they will be giving out gifts. The three main ingredients for a DIY Powerwall are of course the batteries, which will form the battery pack, a decent BMS to protect them from all kinds of mishandling, and of course a suitable enclosure. So let's start off with the battery pack. According to Wikipedia, the Tesla Powerwall consists of lithium-ion cells. Out of such batteries, I already created several battery packs in the past, so this should be an easy job, right? Well, to do this, I firstly calculated the capacity of my original lead-acid battery, which was around 1.2 kWh. For the battery cell itself, I went with the Samsung INR 18650-25R, whose capacity should be around 9 Wh. That means I would need around 134 of those cells, which would set me back around €448. Now that is of course pretty expensive in comparison to the cheap lead-acid battery. But then again, lithium-ion batteries offer a way better volumetric and gravimetric energy density, which means the final battery pack will be much smaller and lighter. But as I was about to order, I noticed that the cells do not perform well in cold conditions, which is a problem because temperatures in Germany can go down to -20 degrees Celsius in winter. That is why I started searching for a more durable battery type alternative and found LiFePO PO4 batteries or lithium iron phosphate batteries. This battery chemistry is known for not only being able to handle lower temperatures, but also for being safer, which you can easily see for yourself by just searching for them on YouTube. Another difference is that LiFePO4 offers a slightly different nominal voltage, which actually makes it more suitable to be a lead-acid replacement. And also the charging voltage is a bit different, but a constant current, constant voltage method is still recommended for charging. However, the only reasonable LiFePO4 cells I found were these, with a capacity of 19.2 Wh at a price of €9.19 if I order 63 of them, which I would require. That would equal around €580, which was a bit too pricey for my taste. Thankfully though, I found those 100 Ah LiFeYPO4 cells at a price of €114. The Y, by the way, stands for yttrium. That is added to the cathodes to allow this battery to work down to -45 degrees Celsius. 4 of those cells in series should not only give me a voltage range between 14 and 11.2 volts, but also a capacity of 1.28 kWh at a price of €457, which seems acceptable. Once again, this battery technology is not as cheap as lead acid, but lies with its better volumetric and gravimetric energy density right between lead acid and lithium ion. So naturally, I ordered 4 of those cells along with suitable terminal connectors and a fuse. After receiving them, I inspected them to make sure that they were not damaged, and then continued by connecting these cells with the terminal connectors according to this diagram, in order to create the 12V battery pack. As soon as I was sure that all the voltages at the battery pack were correct, it was time to choose a suitable BMS, which should at least feature an overvoltage, undervoltage and overcurrent protection, along with a balancing feature to keep all the batteries at the same energy level. Now of course I could have used one of those 4S Chinese BMS, which you can find all over eBay. But it just didn't feel quite right and safe for such a big amount of stored energy. So luckily, after I searched the web for quite a while and only found pretty expensive BMS, I finally discovered the company Energous Power Solutions, which offer the tiny BMS for a more reasonable price. It works with 4 cells of LiFePO P04 and basically offers all the features that I've been looking for, and even more by, for example, offering temperature measurements, analog and digital inputs and partly outputs, and also logging of the battery activities. So after receiving my board, along with all the required wires and temperature probes, I added a fuse to the plus terminal and another terminal connector to the minus terminal, which I then used to connect the BMS B+ and B- solder pad to the battery pack through thick 12 AWG wire. Next, I removed all the wires from the BMS balance connector except the 5 upper ones, which I then either soldered to the terminals or locked them in place with the U-screws according to this scheme. Afterwards, I plugged the balance connector into the BMS and continued by preparing the 2 temperature sensors, securing them in place at the right and left side of the pack, and then hooking them up to the BMS as well. And as soon as I was done securing the BMS in place and tidying up the wiring, the hardware of the battery pack was basically complete. So I hooked up the included USB UART converter to the BMS and a computer and started the given Battery Insider software. There I'm able to define all the max and minimum voltage, current and temperature values, and whether I want to use the dual ports or single port modes. Dual port basically means that my charger and load circuits are not the same, and thus I want to cut them off separately. But since I'm using an MPPT charge controller, which offers a load output on its own, I have charger and load circuit combined, and thus I need the single port mode, which therefore means I have to connect the charge controller to the B+ and C- solder pads. Of course, you can also find all those information in the 76 pages long manual of the BMS, which was actually quite an interesting read. To finish the software part, however, I set the voltage and current values according to the LiFePO P04 profile that my MPPT charge controller came with. And with that being done, the battery pack was ready for installation inside the housing. So after measuring the dimensions of the battery pack, I chose a slightly oversized electrical cabinet. As you can see, it is not only made out of tough steel sheets and thus weighs a ton, but it also fulfills all kinds of safety standards, which is always nice to have. And of course, the battery pack fits effortlessly inside it, which means it was time to drill a big hole in the bottom lid of it in order to mount a cable feed through, and then I continued by drilling 4 holes for the cabinet into my garage wall and then securing it through the help of plastic anchors and big screws. Next, I prepared 2 conduit pipes, which through the help of pipe clamps I then secured to the wall as well. Last but not least, I guided thick wire into the electrical cabinet, placed the battery pack inside it and hooked the B+ and C- pads up to the wire, which I then connected to the charge controller. And with that being done, my rather crude power wall was complete. According to the appliances used in my garage, it also seems to work without a problem, which was also confirmed by my Solar Charge controller app as well as the BMS software. Now granted, my solution is a tiny bit more expensive in comparison to the Tesla Powerwall when we look at the kWh per euro. But then again, I can easily modify it by adding more batteries to not only increase the capacity, but also change the voltage up to 51.2 volts. And with that being said, I hope you enjoyed watching my unique take on the DIY Powerwall project. If so, don't forget to like, share, subscribe and hitting the notification bell. Stay creative and I will see you next time!